This is last year's final exam. I will go through the solution, solve it with you. Question number 1 is actually chapter 16. Although I have to tell you this, okay? Although I say it covers all the chapters, you may not find any direct question from chapter 15. But you cannot ignore chapter 15 when you study, because the whole thing starts with the chapter 15. There may be no direct question, but if you don't understand electric force, electric field, then, solving question from chapter 16, 17, the ideas are there. So that means you have to study chapter 15. Okay. And when I say all the chapters will be covered, but you will not find direct question on chapter 15, like Coulomb's law directly. But, the idea will come again and again in different forms in other chapters. So if you look at this question number 1 is actually chapter 16. Okay. So that's why I don't tell you chapter 15 is omitted. Actually, it is not omitted. Okay. The idea is important. That is a foundation. Right. So question number 1. As an electron moves in the direction of the electric field lines, these are statements. We have to pick the correct one. Only one is the correct statement, others are all false statements. So this is about potential, the definition of potential and potential energy. That's how we start chapter 16. Potential, the symbol is V. Potential energy is, we use, it's energy, PE for potential energy. We first define the potential energy. After that, we define the potential. Potential is, the delta potential is delta potential energy per unit charge. So that's how they are related. So the question here is, an electron, it's a charged particle, moves in the direction of the electric field lines. There is an electric field and a charge is moving in this electric field in the same direction as the electric field. So it is in the direction of the electric field, not the opposite direction, in the same direction as the electric field, an electron is moving. The potential is independent of the test particle. Potential does not depend on the charge itself, whether it is positive charge or negative charge, it doesn't matter. This is what you have to remember. When you travel in the direction of the electric field, potential decreases. It's easy to remember this way, if you know the capacitor plate, potential, we have a uniform electric field. Potential is, the electric field is from the positive charge to positive plate to the negative plate. So which has a higher potential? The positive side. So in the direction of the electric field, potential decreases. Remember this, okay? It is not in the formula sheet. So if you remember this, it becomes easy to answer this question, okay? The potential decreases in the direction of the electric field. Just remember that. Then you can easily answer this question. But this question compares not only the potential, also looking at the potential energy. So let's start with the potential. Delta V means change in the potential, right? So I told you, in the direction of the electric field, potential decreases. Let me take A. This electron moves from low potential to high potential. No, right? Because it's moving in the direction of the electric field. It's given to us. It is moving in the direction of the electric field. That means when you move in the direction of the electric field, it doesn't matter whether it is an electron. Does it matter? No. For the potential, the test charge doesn't matter. The potential will decrease if you move in the direction of the electric field line. So this is wrong. You don't even have to worry about looking at the potential energy, because the first part is wrong. So I can delete it. What about B? Same story. It's saying the opposite thing. It's saying you are going from low to high. No. When you move in the direction of the electric field, you're actually going from high to low. That is also wrong. Now I'll skip this and go to this one. It seems to be correct, at least the first part, high to low. When you move in the direction of the electric field, independent of what kind of charge we have, it doesn't depend on that. The potential is only a property of the electric field. It decreases, so this is correct. Well, at least the first part is correct. What about the second part? Now we come to that. So if you know about the potential, we know that potential energy is related to the potential through this equation. That's how we define the potential in terms of the potential energy, right? If delta V, we know it is negative, right? Because we are moving in the direction of the electric field, that means potential is decreasing, delta V is negative. For this particular example, not in general. Q is an electron, negative. Negative will become positive. That means when you move in the direction of the electric field, for an electron, the potential energy will positive mean increases, right? Final potential energy is greater than the initial. So potential energy increases. Now we have to select between these two. This is also correct for the potential, high to low. But this is wrong because the second part is wrong. And this is correct because both parts are correct. Gaining electrical potential energy. So that's what we found out. Delta P is positive, mean potential energy is increasing. Done. Next question. Yeah. Yeah. Suppose I said proton, then the answer will be D. Question number 2. The uniform electric field E of magnitude 200 Newton per Coulomb is directed toward the right, A to B, as shown in the figure. These 2 points are separated by a distance of 0.3 meters. What is the change in the electric potential as we move from A to B? Now, we have an equation for a uniform electric field, okay, only for uniform, this is a uniform electric field. We have the equation, it is in the formula sheet, which relates the potential to the electric field and the displacement, which is this. The change in the potential, this is for a uniform electric field, is E dot D, the scalar product between the electric field and the displacement. So it depends only, it doesn't depend on the test charge or anything. If there is an electric field, we can talk about the potential at any point. So the change in the potential will be electric field dot product with the displacement. So dot product mean what? Magnitude of E, magnitude of D, cosine of the angle between these two. Now we have the electric field like this, and you are going from A to B, so the displacement is also in the same direction as the electric field. You are moving from A to B. Displacement and the electric field in the same direction. What is the angle between them? 0. Cosine 0 is 1. So delta V will be minus is already there here, E dot E multiplied by D. All you have to do is to just substitute and get the answer. E is 200, is a SI unit, always take care of the unit. D is also SI unit, so we have no problem, and that will be this. Done. Question number 3. See, these questions are direct question, easy. 2 point charges are placed as follows, as in this figure. These are the 2 point charges. One is positive, which is in red. Other one is negative, which is in blue. Q1 is plus 2 microcoulomb. Q2 is negative 3 microcoulomb. And their positions are given. This is at 0, 0. This is at 0.4. So this is 0.4 meters. And the question is, find the potential, the total potential, because we have not one charge, we have two charges at the point P. At this point, there is nothing at the point P. It's just a point, okay? At that point, what is the total potential? This is the question. So again, you need to know the formula. The formulas are there in the formula sheet, but if you don't know what we are talking about, you know which formula to pick. Although, yeah, I have to warn you one thing. In formula sheet for midterms, you have the description. So even if you forgot the theory, you know, when you read it, you know which one is for which. But for the final exam, because we have so many formulas, I'm sorry, I know, this time you just can't depend on, you need to remember that, right? But you will see the formula. Then if you have studied, you will remember very quickly. If you didn't study, of course, you would not remember. Okay, so there's a potential. The previous one, the equation for potential is this. This is for uniform electric field. That is for uniform electric field. But then here you are talking about point charges. Then there will be another formula because these are point charges. It's not a uniform electric field. For a point charges, the absolute value of the potential, not delta, is given by this equation. So, you know, you will see in the formula sheets there are so many potential V. If you don't know which one to take, then we have to study the concept. Okay, it is not just a, you know, there are formulas, you know, you substitute the value and find the answer. That is not physics. You need to know the physics. Okay, so you know which equation to pick. So this is the formula for the potential from a point charge. So this question is about point charges. We don't have just one point charge, you have 2 point charge. Each of these point charge will give a potential at this point. So from this, if I call it Q1, we can say there's a potential V1. And this guy will start another potential, so that will be V2. So the total potential will be the sum of these two. But unlike the electric field, which is a vector, electric field is a vector. That's become difficult because you have to worry about the direction. It's 2 dimension. You have to add the x's separately and the y's separately. But for potential, we don't have such problem. It's a scalar. Potential is a scalar. But again, yes, it is a scalar. But this q has to be substituted with the correct sign, because potential can be negative if the q is negative. It doesn't mean it is a direction. It's not a direction. Like temperature can be negative depending on where you put the zero value. So likewise, the q, because q can be positive or negative, that means potential can be positive or negative. This k and r are magnitudes. Okay, r is a magnitude. It is not a vector. It's a magnitude. The distance, straight line distance from the. Let me explain. What is this k? K is the Coulomb constant. If it is not in the question, don't worry, it will be in the formula sheet. R is the distance from the charge to the point where you need the potential. So now I can get the total potential. It will be V1, that means potential from the charge 1, plus V2, the potential from the charge 2. So V1 will be K Q1, the distance to the point. So this distance, right? Do you know this distance? Yes. The point P is located at the 0.3. That means this is 0.3. So we know, but I'm not going to do anything. I will just call it R1. I will not substitute. I'll just put the symbols. Plus, the potential from this guy will be K Q2, divide by this will be the distance from the charge to where the point is. So this will be R2. Okay, yeah, I'll come to that later. So let me put it like that. Now we got the expression. All you have to do is to substitute the values and calculate using the calculator. I'm going to do one thing, which is, yeah, let's substitute. But, to make the calculation faster, I find this k is happening in both places. You know about common factor. Yeah. So I'm going to take it out. It will make the calculation faster. That's why efficient, more efficient. Now let me put the values. I'll not put the value for this, it's long. So these are the one you need to make sure we don't make a mistake. Q1 is +2, but it is in microcoulomb, right? The answers are in kilovolt, but we don't want to mix up things. So let us put everything in SI unit, get the answer in volt, then we can later convert it into kilovolt. So 10⁻⁶, micro mean 10⁻⁶. R1 is 0.3 meters plus Q2 is minus. This is where you have to be very careful. Don't ignore the sign. Potential can be negative. Okay, it is not a magnitude thing. It can be negative. So you have to put the negative sign. If you don't put it, you get everything wrong. It's a multiple choice exam. You cannot say, I forgot, you cannot say that, because either you get it right or you don't get it right. Either 1 or 0, nothing in between. Divide by R2. Is it given? No. This is given, this is given. It's a right angle triangle. So, we can apply Pythagoras theorem. So, you have to remember 3, 4, 5. Sometimes become handy, you don't waste your time. So that means, this is 0.5 from Pythagoras theorem. So that's it. Now, don't waste your time in calculating. You should know how to use your calculator very effectively without wasting the time. So let me also take my calculator. Okay, this is my calculator. Oops. What did I do? Yeah, sure. Come on, why are you interrupting me? There will be class, I cannot cancel the class, but I will not take attendance after today. Yeah. Yeah. After the break also there is a week, okay? 1 week. After the break, there is only 1 week. Also, Sunday is holiday, I think. No, Monday, Sunday, Monday, both holiday. So we don't have a Monday class. We only have the Wednesday class. Right. K. It's in the formula sheet. Okay, maybe not see it. This is the K value. You don't have to memorize it, but it helps if you can memorize it. So you don't have to, about 1 second, 2 seconds, you will save. It matters in an exam situation. Multiply, bracket, use the fraction, Muhammad. 2 10 to the power minus 6. Bring it down 0.3. Right up. Now, this is minus here, right? I can bring it and call it subtraction. Sometimes you can do these things. Okay, you don't have to put bracket, the same thing. Then the fraction again. Now you don't put this minus again. Okay, so be careful. 3 exponential minus 6. Bring it down 0.5 close the bracket, ups, that's wrong. I had to bring it up, okay, it doesn't. Close the bracket, right, that's it. This is not an equation solving, it's a direct calculation, equal sign. You have to press the SD thing. So that's the answer, 5,993. To two significant figures, it will be 6,000, which converted to kilovolt will be 6.0. Okay. Right. This is no numbers here, this question. You have to get the expression. What is the question now? 2 point charges Q1 and Q2. So let me draw them. There's a charge Q1 and a charge Q2. And the distance between them is R1. So when you have two charges like that, it will have a certain energy, because, when you bring it close, there may be attraction, repulsion. If it is a repulsion, you have to keep it in place. So there'll be a lot of energy there. So the energy, potential energy. So this will have the expression for the potential energy for two charge configuration is this. You need to remember this to answer this question. Well, it will be in the formula sheet. Okay, but if you don't know which formula to pick by reading the question, then it's a problem. That's why you need to know the physics. So we have two charges separated by this distance between them. What is the minimum amount of work needed to make the distance between them? You have, now, for the same two charges, I'm going to change the distance, move it closer or apart. I don't know what it is in general. So R1, I make it R2. Maybe it is smaller or bigger. Just in general, I'll call it R2. So this one energy initially, this is the equation. So initial energy PE1 or PEI will be K Q1 Q2 over R2. Now this is the PE initial. Now the energy changes. PE final will be, because we are changing the distance. Others are not changed. So it will be K Q1 Q2 over R2. Same Q1 Q2, only the distance changes. How much work you need to change the energy from PE initial to PE final? That's the question. So you know that work will be either you need to change the kinetic energy, both, right? If we are changing potential energy, so if there are no other energy involved, so in atomic, we can ignore the gravitational potential energy, because for particles, point charges, they don't have mass, right? Ideal. So it will be, this is the equation. The work done is how much change you made into the kinetic energy, how much you made into the potential energy. Here we are not changing we are moving it slowly, okay? It's always at zero speed. So no change in the kinetic energy. So the only work you need to do is to change the potential energy. So simply the work done will be PE final minus PE initial. So that's why this is the answer. This is PE final and this is PE initial. No numbers, just the expression. Number 5. A 0.81 microfarad capacitor and a 1.20 microfarad capacitor are connected in series to a battery of this. So let's draw it. So we have capacitor 1, which is 0.81 microfarad, and capacitor 2, 1.2 microfarad, connected in series. And then they are connected to a battery, which is 310 volt. So this is the story. Now, there will be charges on this, right? This capacitor and that capacitor. It will be the same charge. So it's positive. It will be plus Q on this plate, minus Q on this plate. The same plus Q in this plate, minus Q that plate. Because they are connected in series, it will be the same charge. Our question is to find this charge. charge on any one of these plates, it is the same. Irrespective of the plus minus, the magnitude is the same. We are supposed to find it. How do I do that? We know they are the same charge, so I will get the equivalent capacitor of these two, and the charge on the equivalent capacitor will also be the same. Combine them. If two capacitors are connected in series, how do I get the equivalent capacitance? Now, remember parallel series. There are formulas. And we also do it for the resistors as well. The formula you have the capacitor is not the same as the formula you have for the resistor. They switch places. So when capacitors are connected in series, what do? It will be C1 inverse plus C2 inverse and the inverse of it, right? That is in series for capacitors. Now we have in series and they are capacitors. So tell me, shall you do it? 0.81 inverse plus 1.20 inverse, add the inverses and take the inverse of that. Somebody help me, give me the answer. Give me two more digits. Don't round it like that. 483. Yeah, I remember because we did it before. Right. No, please do not round, okay? At least keep three significant figures when you move from. Don't round too much. So this is 0.483. What is the next step? I want to now, we have reduced it to this one. Now it is easy because you have just a capacitor and you know the one capacitor, you know the potential, the voltage applied is 310. So you have the definition of the capacitance, which is this is the definition of capacitance, is equal to charge on the capacitor divided by the potential difference. That means charge will be, all you have to do is to substitute the value. See, we know for the equivalent capacitor, right? Because multiply by delta V, which is 310. So that should give this answer. Please check. About the units, okay, I forgot to. Yeah, because I didn't. Is microfarad SI unit? No. I didn't bother to convert it because if I put this in microfarad and this in voltage, the answer will be microcoulomb. The answers are in microcoulomb, not in coulomb. So that's fine. Okay. Number 6. A charge of 5.6 10 to the power 19 electrons, is the number of electrons, not the charge, flows through a conductor over a time interval of this much time. What is the current? So what is the definition of current? That's the symbol for current. What is the definition of current? If you stay there, you take an area and count the number of charges passing that area, divide by the time taken from a certain amount of time, the rate of how fast it is flowing, that is the current. So delta Q divided by delta T. The rate of charges passing through a given area, that will be the current through that area. That's the definition. So you are staying at place and you are looking at the electrons passing. Electrons, a number of electrons, but each electron has a charge. So the charge will be the number of electrons multiplied by the charge of one electron. Yeah. So this will be the amount of charge. He didn't give us the charge, he is only giving how many electrons are passing. but each electron will have a charge of E. You know what is the value of E? It's given there. Okay. If it's not given, you can get it from the formula sheet. So n, the number of electrons multiplied by the charge of one electron will be the total charge that will be flowing past that area. So we get the delta Q, divide by the time, 2.8 seconds, then you get the answer. So, you can just check it yourself. You should get the answer because everything, Coulomb is SI unit, second is SI unit, so Coulomb per second is amperes. So you'll get the answer in amperes. It's given in the question. This many electrons, that is a number. Okay, so he's saying a charge of, it's a bit confusing, the word, a charge of 5.0 electron. It should have write 5.6 in the minus 19. So many electrons are flowing through. Okay. Anyway, I hope it is understood. So many number of electrons are passing through. This is not the charge, it's the number. Number 7. This is a question that repeats again and again. You know the answer to this, right? When you put the switch on, the bulb lights immediately. Can you say the electrons that coming out of the battery has to move and come to the bulb in order for the bulb to light? No, it's not like that. The moment the switch is on, the electric field will be traveling to the bulb at the speed of light. So when the electric field reaches the bulb, the electrons in the bulb will move. Okay, you don't have to wait an electron from the battery to come all the way to the bulb. So that's why when you turn the switch on, it lights immediately. So the reason is that it is determined by the speed of the electric field, and speed of the electric field is the speed of the electromagnetic wave, c, the speed of light, the fastest speed possible. Question number 8. Statement question again. Voltmeter, ideal mean perfect, okay? We don't have ideal. If a voltmeter to be a perfect voltmeter, it should have an infinite resistance. Then only the reading will be most accurate. So that is a condition for, if you want a good voltmeter, you have to make the resistance of the voltmeter as high as possible. So it will draw very minimum current without disturbing the circuit. At the same time, for an ammeter, is the other way around. The perfect ammeter should have zero resistance. So it will not introduce any resistance to the circuit. So it will not modify the current that would flow if you don't have the ammeter. So yeah.
I think E is either correct, any value, but not the infinite.
Ideal, you're talking about ideal. Infinity means the resistance of the voltmeter should be very high, right? Infinitely high. Not any value. I mean, we don't have, can you have infinite resistance? No. You have a certain value. So we are talking ideal. You know the meaning of ideal. Okay. Perfect. Practically, we cannot have it. But, if you want a really good voltmeter, you should have infinite resistance. Okay. And ammeter should have zero. It's also ideal. You cannot never have a zero resistance. There will be some resistance. Number 9. In the circuit shown in the figure, the current I1 is given. And the current I2 is not given. Resistance R here, this is also given. Now, find I2. This is the question. Yeah. The answer is 3. Current is I1, total current. I1 is 6, I2 we find. I didn't follow you, what you are trying to, yeah, okay. Right, how do you solve this question? Coulomb's law? Coulomb's law for L. Oh, yeah, but is it just a formula you remember? You have to tell the logic. Yeah. No, okay. Let me help you. A and B. Okay, and let me call it C and D. Can I say VAB is equal to VCD? Why not? A and C are the same potential. Do we have anything in between A and C? No. Here, this in this is a zero resistance, right? So that means there is no drop here because we say it's a these wires are superconductors. Zero. Practically, it is not so, but we can imagine that A and C between A and C is a superconducting wire. So we ignore the resistance of these wires. So from A to C, there's no potential drop. So the potential at A is equal to potential at C. Similarly, B and D. That means VAB means what? The potential difference across A and B is equal to the potential difference across C and D. Okay, this is the thing that we use now. The potential drop across resistance 2 and the potential difference across the resistance 4, they are parallel, right? They are parallel. It's very clear they are parallel. So voltage across 2 ohms and the voltage across the 4 ohms is equal. And from Ohm's law, voltage across AB will be I1 into 20. The voltage across 4 ohms will be I2 multiplied by not 20, is it 2? Yeah, 2, and it is 4. It looked like 0 for me. Okay, right. So this is the principle. Okay, you cannot just memorize the equation without knowing because somebody solved this for you and you are going to remember, okay, I1 R1 equal to I2 R2. It is not going to be the same every time. If there is a another resistance here, can you say I1 2 is equal to I2 4? No. Okay. So now you have the answer, right? I1 is given 6. And I2 is the unknown. So I2 should be 3 for this to be true. Can you solve it? Number 10. We have bulbs, they all identical, same resistance. That's what you mean by identical. They all have the same resistance. And you have batteries, they have it's identical, same EMF. Now, the question is the total power produced by the battery. You have to rank them from the lowest to highest, the power from the battery. When I was doing this question with the other section, the morning section, I didn't read the question. I just looked at it and said, oh, he's asking about the brightness of the bulb. I made a mistake, okay, because I wasn't careful with the wording of the question. Is the question talking about the brightness of the bulb? No. How much power delivered by the battery? So you have to be very careful because we are used to some question where talking about the brightness of the bulb, right? When you see this picture, you jump at it, oh, he's asking for the brightness of the bulb, and that's a different answer. The question is the power delivered by the battery. So the power is I delta V. So it can be shown it is the same as I squared R if you know the current and the resistance. It's all the same as V squared over R. But we are going to get this because the delta V is the same for all. It is the same battery. Delta V is the EMF of the battery. The I is going to be different. Here, let's say is I, which is equal to E over, say they all are. E over R, right? If I call it I for the first guy, for the second guy, do you think the I will be more or less? More? The resistance is doubled. They are in two resistances in series. So the current will be halved, less. So if the current is I here, the current through this guy will be, from this battery will be I over 2. Here, when you have two resistors in parallel, the resistance will be halved. So the current will be doubled. So if the current is I here, the current here will be I over 2. The current here will be 2I. Now you have the answer. Who will be producing the most power? C. Lowest. Okay, let me. Who will be producing the lowest power? B. Yeah, okay. Right? Because it is, this, the equation is this, right? I into. So you have to just look at the I. Smallest I will be B. That will be the smallest power. Second smallest will be A. The highest will be C. Yeah. Yeah. Okay. Maybe I have an idea to give a question. Right. Suppose the question is not about the power delivered by the battery. Which is the brightest? Which is the lowest brightness? Now you need to use this equation. Why? We know the resistance. We know the because each bulb, right? We know the I and we know the resistance. I would, yeah, okay. So tell me, which is the lowest brightness? R is the same in all bulbs. So you only look at the I. So the lowest brightness will be R, yeah, I over 2. That will be the same. Next will be, both of them, will have the same brightness, right? Because R and the I is the same. And R is the same in all 5 bulbs. And the current maximum will be C. So the order will be, A and C will be the same brightness, right? No. 2I. Yeah, you know what happened? There will be I through this and I through this. This I, 2I will be divided into I and I. Do you understand what I'm saying? So both A and C will have all the bulbs of A and C will have the same brightness. So the answer would look like this: B, then A, C. It doesn't matter which you put first. Okay? Right. You can also look at from this and answer the question. R is the same. R is the same. But for this guy, the V here will be V over 2, and for this also V over 2. So that will put this one is the lowest brightness, and this A and C same brightness. Question number 11. When a 22 ohms resistor is connected across 12-volt battery, a current of 485 milliamperes flows. The internal resistance of the battery is. So a battery, a practical battery, will have an internal resistance inside it. So we can say a battery, perfect normal battery, will be broken into 2 parts. An ideal battery with the voltage of V and an internal resistance R. And this is connected to a load, outside resistance. So this is what the question is talking about. You have a battery with its internal resistance, and it is connected to an external resistance R. So we apply the circuit. So Ohm's law, E is equal to IE, but you don't not only have this resistance, we have two resistance. There is a hidden resistance inside the battery, which we call the internal resistance. So this is the equation. So in this question, E is given. Sorry, this is not E. R. R, the big R, and E is given, and the current is given. Only unknown is the small r. So it's a matter of just answering it. Always use the calculator. Don't worry about the algebra. Okay, we don't care. We have a calculator. Let the calculator do the algebra. So take your calculator. Just put this in. E is equal to what? 12 equals I. I is milliamperes. Okay, so be careful. So convert it into amperes. 0.485. Multiply, open a bracket, R is 22 plus this is your X, alpha X. Close the bracket. Just don't bother to do algebra. You just write the equation and tell it to solve. I know it's a simple algebra, but still, why bother? I mean, it will be faster. You will less likely to make a mistake if you know how to use it. Okay, so you should have practiced it. This is not the answer. You should see the L minus R and X equal to. So this is 2.74. Good, you got it. Number 12. An ideal EMF source of 24 volt is put in series with this. These are in series. What is the potential difference across this? This is the question. If I know the current, the answer is simple, right? So delta V4 will be the same current is going through all of them. So that current multiplied by 4. But do I know the current? No. So we must be able to find the current. That's easy. This is a very simple circuit. You can replace the whole thing by just one resistor. And if I know this resistor, the equivalent, then you can say the current is equal to 24 divided by that resistance. Can I find this equivalent resistance? Easy, right? It is, 2 plus 4 plus 6, which is 12. So current will be 24 divided by 12, therefore 2 amperes. Now you bring that 2 and put it in here, you get the answer. Quite fast. I know I will finish as maybe 2 more questions. Let's see this one and that one. Okay, we will stop. Loop rule. So Kirchhoff's rule, when the circuit becomes complicated, Ohm's law is difficult to apply. You cannot. We need these rules. So there are 2 rules. One is called the junction rule, which is a statement of conservation of charge. And you have the loop rule, which is the statement of conservation of energy. So that's why this is the answer. Okay. Question number 40. Okay. Yeah, probably we will stop with this. Question number 40. Now we are going to apply the loop rule and the junction rule together in this one question. The question is to find this E1. E1 is not given. You are asked to find it. What is given to us is the current in this segment, this blue wire. Let me make it blue, paint it blue. So everywhere in this blue wire, it's the same current, right? There's no branching within that. And let me take another color. And what about this red segment? Can I say everywhere in the red it is the same current? Yeah. There is no, it's a bend only. It's not a junction, right? This is not a junction. C is not a junction, it's a bend. So it's the same current everywhere, I2. What is left is a black one. Do I know the current? In the black, let me make it another color so it's easy for me to refer to. This one. In the green segment. Is that one current everywhere in the green segment? It's not given. It's one current. There's no branching. Everywhere in the green wire, it is one current, right? There is no division, right? No branching, right? So, in order to find E1, I need to take a loop, right? There are many ways of taking it. I can take this loop, okay? Or I can take this loop, or I can take the outer loop. Okay, I have three choices. Is this given? No. So this loop is out because I need E3 also. This loop again I need. The only good thing is to take this outer loop. That means you start from A, go to B, go to C, go to D, and go to E, and go to F, and come back to A, the outer loop. In the outer loop, do we know the green current? We don't know, but we can find it. So this question you have to apply the junction rule to find I3. After finding I3, you apply the loop rule for this big loop, outer loop, and find the E1. Because E1 will be the only unknown once I know I3. There are no other unknown when you go around. This is given, I2 is given, and all this voltage is given, EMF is given, this resistance is given, this resistance is given, only unknown is E1. Okay. So we can solve it. So let's solve it. First, let's find the I3. Okay. Go to the junction, this junction. And you say sum of all the current, or you can say current in is equal to current out at the junction B. So imagine you are standing at the junction B and looking at the current. I3, I choose it going like that, right? I3 is coming in, right? So this side, plus I3. And I2 also coming in. I3 is going out. Oops, I'm sorry. I'm confusing the label. This is already I3, so I have to call this I1. All right. So I cannot use the same label for that because I2 and I3 is already given to us. So I have to call it I1, not I3 again. So I1 is the not known for us, so calling I1. This is given, this is given. How much is I1? I2? I2 is how much? 5. And I3 is 7. So that means I1 is equal to 2. That's it's not a difficult thing, because although it is rule, you can see why it is. See, there's a 7 amperes here. Here is 7 amperes. This I3 is 7 amperes. I2 is coming in. How this become 7? Somebody has to give another 2. That means I1 is equal to 2 amperes coming in. Right. So we know what is I1. It is equal to 2 amperes. Next step is to apply the loop rule. What is loop rule? This is loop rule. What is your loop? You go from A to B to C to D to E to F and back to A, the outer loop. I'm going to take the outer loop. Let me start from A. When you go from A to B, is there a potential change? Yes, we got a resistor. So you know from Ohm's law, the potential change will be current multiplied by resistance. Current is I1, which is 2 amperes, and the resistance is 4. But you have to pause. This is just a change. We don't know whether to put a positive or negative. This is very important, okay? IR, yes. Y positive, Y negative. Yeah. No, it is same direction. You are moving from A to B. That is your motion. Current is also in the same direction. I found it is to be this direction. So you are moving in the same direction as the current. Then you have to remember, you can just mechanically remember, but you should know why. You should be able to tell, just remembering like a recipe is not good. Can you tell me how I know it is negative? Yeah, that is a recipe. But that's not the physics. It's just you're memorizing. It's not the physics, yeah. Current flows from, that is the physics. Current flows from high potential to low potential. So you look at the current to know whether you're going from positive to high to low or low to high. I don't know. When I go there, I know it is this. The magnitude is 8 volt. But whether we are decreasing or increasing, you know by looking at the current. You know current flows from high potential to low potential. That means your potential is decreasing. Therefore, I put the negative. Okay. Now, from here to here, anything? No. Here you come across this battery. You are jumping from the positive terminal of the battery to the negative terminal. Positive potential is decreasing. So, minus 24. Then you come across this. What is the current through this? I2, right? It is the same. I2 is going the opposite direction to your motion. That means positive. Why? You know the current flows from low potential to high potential. That means you are going from high potential to current moves from high potential to low potential. That means you are going from low potential to high potential. So positive. So that will be 5 multiplied by 7 plus. Anything here? No. Here, the current is this way, right? Same direction. So minus, same direction as your motion. What is the current? I1, which is 2. And here is the unknown. You are moving from negative to positive. So it is plus equal to 0. So you got the equation. The only unknown in the equation is E1. So you take your calculator. Yeah, let's do it. Okay, let's do it. So where is my equation? So just put this in. So you can put the negative sign because that happens to be the first guy. 2 multiplied by 4. Then you have a subtract 24. Then you have plus. You can do it in your mind. Anyone knows what is 5 into 7? 35. Okay. You can save time. Just write in 35. Minus 8. You don't have to do the multiplication. Do it manually. Plus x equals 0. That's it. Now you solve it. Shift, calc. This is not the answer. This is from the previous operation. 5. Okay. So, right. I will stop now. Let me take attendance. Okay.